Okay. All right, guys. So what we are about to do today is just to once again bring you guys sort of up to where we are, and we are going to use this exercise to review what we have been doing. All right, starting from heat work until we got to the first law of thermodynamics, see the processes, combine them into a heat engine and how it works, define efficiency, and talked about the best engine in the universe. And now we are going to, practice and see how it goes. All right. We have done a couple of them last time. All right. And it's sort of like it's kind of big because when I say big, it means there's so many things that is going on in the thermodynamics calculation. There's relationship here, equation there, on and on. All right, but anyway, once you have done this a couple of times, it seems like, well, it's not too bad, I hope. Yeah.
Okay.
All right, so let's dive in. And all right, I want you to just sort of like practice this along with me, or if you can do it in advance, it will be really nice. Okay, so I'm gonna go very slowly on this one because I think this will give you sort of like a grand conclusion of what we are doing. Okay, even though the question is so simple, like, hey, we have a PV diagram. You are shown that cyclic process, 1, 2, 3, 4, on and on. And the question is simply asking you what is the thermal efficiency of the engine? And assume that there are n mole of monatomic ideal gas. And let's go from there. All right, but anyway, I'm going to talk about everything that we have been doing. All right. Of course, calculating the efficiency will be one of them, but we're going to do sort of everything that we have done in the past. Okay. All right. Let's get things started here. First, start from 1 to 2. Okay. So let's do from 1 to 2. So let's do a detailed calculation here one more time, shall we? All right. So it's a constant volume process, no work done. 0. W is 0. So from the first law of thermodynamics, delta U equal to Q minus W. So W is gone. So we're kind of familiar with this one. The amount of heat that flow into the system will go into the internal energy. So that's why the delta U, the change of the internal energy, will increase. Chill. All right. And we knew from the equation of states and gas equation, and from everything, that the internal energy of an ideal gas can be calculated using U equal to 3/2 nRT. So the delta U is 3/2 nR delta T. Okay, temperature is the signature of saying that, hey, is the internal energy of the system is going to change or not. Okay, if temperature rises, U rises along with the temperature. Okay, and just to remind you, we rearranged this one to make it look like this before, if you like. So that means in a constant volume process, the amount of heat flow can be written in terms of the molar specific heat, C sub V. Okay, so that's a molar, it's a heat capacity per mole. All right, so is this a good review? Okay, so far so good. All right, so a couple of things. Okay, every time that we see PV diagram, imagine that we have an isothermal line all the time. Something like that. All right, 2 and 4 might not be on the same line, but just accidentally. Somehow are we having a problem? Try to avoid this, but I don't really know are they at the same temperature or not. But assuming not, 2 and 4 is supposed to be on a different line, I guess. Who knows? Okay. All right. So jumping from 1 to 2, so kind of you can see that, okay, you're jumping from a lower line isotherm to a higher isotherm. So delta U is supposed to be positive, as indicated over here. That's as expected. So the delta U is supposed to increase along with it. Okay. All right, let's calculate. So the N is given, the numbers, everything is good. And now you can read from the scales over here along the X and Y axis. So, okay, go ahead. All right. So delta U, which is Q, is going to be 3/2 N T at 2 minus T at 1. with me? All right, the change of the temperature is going to be final minus initial. Anytime you see the change, you take the final state, subtract out the initial state at all time. So you're going from 1 to 2, then it means you take the final temperature, subtract out the initial temperature. But then we use the equation of states again because you don't have the direct information about temperature, but that's okay. PV equal to nRT. Oh, I think I'm missing the R. Sorry, guys. Okay, let me squeeze it in here. NR. There we go. All right, so PV equal to nRT. So that means 3/2 is still there. I can write this as a P2V2 minus P1V1. All right. And you guys know that the V1 and V2 are the same. So that's no big deal. All right. And the rest, just read from the scale. The volume stay fixed at V naught. P2 is 2 P naught. P1 is P naught. So it's going to be 3/2. Over here is 2 P naught V naught. Subtract out 1 P naught V naught. So what you have left over here is going to be P naught V naught. Very good.
Okay.
Done. That's it, guys. Is that going along really well? Seems like doable. All right. I would like to go pretty like, sort of like moderate pace today because this is like a grand conclusion of everything. So I just want you to be able to pick up this one just one last time before we finalize the other stuff in the first module right here. Okay. All right. Notice Q is positive or negative. It's positive. Numbers already been taken care of. I mean, the sign of this number has already been taken care of. So that means there is going to be a heat flow in. Let me write it like this. Let me call this Q12 then. So I can put subscript over here to be 1, 2, 1, 2. With me? All right. So signify that we are looking at just the segments 1 to 2. All right. I think that's pretty much complete everything that's going on between point 1 and point 2. So far, so good. All right. Oh, there is a question comes in. Oh, okay. That's about the homework submission. So don't worry about the homework submission. I will prepare the Google form for you guys. All right. But for now, just practice the homework and everything. I just posted the homework set 3. And I think at the end of today's lecture, I'm going to post homework set 4 as well. Okay. All right. Just practice. And then once you have those answers with you, just submit the Google form. As we already agreed, just submit anything.
Okay.
Just showing that you care. Okay, guys. All right. Get going. All right. So that's done. Let's move on to 2 to 3. 2 to 3. Alrighty. Let me change the color a bit just to make things a little bit contrast here. All right, guys. From 2 to 3. It's a constant pressure process. We have done this so many times. Okay. But just to practice one more time, we start from the easiest one. The work is the area under the curve. So that means all you need is just, get down here, get all the area underneath. That will be the work done from 2 to 3. With me, guys? Okay, so this one may be a little bit too messy. So I'm just going to show you by using the highlighter. I think maybe that's better. Let's do the green. So the area under the curve is going to be this one right here. There you go. The green area. All right, just let me know if you got confused or you have any questions. Just, make sure that this is like, think of this lecture to be like, AMA, ask me anything. Yeah. Type of thing. Okay. So the area under the curve, that's easy to do. It's just the width times the height. The height is going to be this whole thing here. Okay. And the width is going to be this right there. So it's going to be 2p naught. All right. And don't forget, it's actually, okay, sorry. It's supposed to be a review. So work done is integral P dV. Okay. So pressure is constant. So make this integral easy. So what you get is this P, V, and then you put V final, which is V at 3. And then V at 2. And then you go to V at 3. So that is a P delta V, which is P at V3 minus V2. All right. So that's a review of how you calculate the work done And because P is constant at 2P naught, and the volume go from V naught to 2V naught, so the change is going to be another V naught. So that's it. It's 2P naught V naught. Is it positive or negative? Well, John, it's positive. Very good. So that means heat flow into the system in this case. So that means during this process, there's another heat flow in. So just to make things a little less confused, so let me put the subscript 2,3 in there. I'm sorry. I'm not there yet. Sorry, my bad. This is work done first. Sorry. W is positive. This is because the volume is expanding. Sorry, my bad.
Okay.
Haven't done, not there yet. All right, so work done is positive because the gas expands from V naught to 2V naught. So, I mean, you can sort of pretty much add the positive side just to emphasize that work done is positive. All right, and then we can put subscript over here. It is a work done from 2 to 3. All right, now move on. Next step, what we can do is just, all right, then delta U. That's easy because it's 3/2 NR delta T all the time. So that it's going to be 3/2 NR T final. It's going to be T at 3, subtract T at 2. Okay, even though we don't have the temperature, but that's all right. nRT equal to P times V. So it's going to be 3/2 is still there. And you put P at 3, V at 3. That's for the first term. Subtract out with the P2, V2. Very good. All right. Now it's easy because P are constant throughout this 2 to 3 process. So you can pull out that pressure, and that is 2P naught. That's fixed. The pressure is constant at 2P naught. And what about the volume change? Same thing. You're going from 2 to 3. The volume change is V naught, positive. All right. So at the end, this is what you get. 3. Let me put this 3/2 for now. I just want to show you something here, just to remind you what we did. All right. So at the end, the heat, it's going to be delta U. I move W to the other side to be next to the delta U. So it's going to be delta U plus W give you the Q. And that is going to be 2P naught V naught plus 3/2 times 2P naught V naught. The reason I'm writing it like this is because, yes, you guys seem to agree with me. That is going to be the factor 5/2. Remember this 5/2? Okay, we have a sort of like a shortcut that you can jump right into the heat if you want to in the constant pressure process. That during this process, you can say the heat during this constant pressure process is going to be 5/2 N R delta T. And that's exactly what we have right here. With me?
Okay.
Okay, guys. Let me highlight here a little bit. 5 NR delta T is the same thing as 2P naught V naught right there. It's going to be the same. All right. So just to signify that this is what we are looking at during the segment 2-3. So I can put the subscript 2-3 everywhere if I want to. And as you can see, the final result, this is positive number. So when the final result is positive, means during this process, there is a heat flow in to the gas. Woohoo!
Okay.
That's kind of long, but that's, I hope you can see that it's doable. It's doable. Very good, very good. So far, so good, guys. No response right here, so not so sure. Next. All right, guys. Can you move on from 3 to 4? Should be easy now. Yeah, let's do it quickly, shall we? All right, guys, let's do it. All right, you guys go ahead. I'll give you like a minute head start here. 2 to 3. Now we go from 3 to 4. All right. So from the look of it, it's just going to be like, Adan, it's going to look exactly the same as before because it's a constant volume again. Okay, so if you really like, now we have sort of like already reviewed what we did before. I can just say like this, guys, from 3 to 4, it's a constant volume. It's going to be NC sub V delta T. Yes. And it's just 3/2 N T final minus T initial. Yes, very good. And once again, because we don't have information about the temperature, but that's all right. It's just gonna be, I'm missing the R again, sorry. Let me squeeze in the R here. NR delta T. Here we go. So what you have is nRT is just a P times V. So it's going to be 3 ½ P at 4, V at 4 minus P at 3, V at 3. Yeah? Very good. So you just have to get here. What is the P? P naught. What is the V? 2V naught. And then you subtract, and then you subtract out what is happening at P3V3. So you say, hey, what is going on with this 0.3 right there? So let me highlight there. Okay. So you read again, it's 2P naught, 2V naught. Yeah, just, read it out. Just read the information out. Okay. So what you get from here is going to be 3 ½ Okay. P4V4 is going to be 2P naught V naught. You guys with me? Okay. And focus on point number 3. P3V3 is going to be 2P naught 2V naught. I mean, whatever you want to do, you can say, hey, John, it's constant 2V naught. You can pull it common factor out and everything. Okay. All right. And at the end, what you have over here is, what is that? 2 minus 4. So it's -2. And then you subtract, divide out the 2. So what you get at the end is going to be -3 P naught V naught. Am I right?
Okay.
Just getting blurred a little bit here. It's just like, okay. I think I got everything correctly written down. Okay, let me double check. Okay, P at 0.4 is 2P naught V naught. PV at 0.3 is 4P naught V naught. Okay, so once you subtract it, you get a -2. 2 and 2 cancel. You get number 3 left on top, and that is your -3P naught V naught. Okay. All right, so there's a quick question comes in. Why is the 5½ again? Okay, so when you go back here in the constant pressure process, here we go. So think of it, I have like a factor 1 right here in the front. Here. Okay. Think of it like I pull the common factor 2P naught V naught out. So the number that's left in the front is 1 plus 3½ So you add it into 5½ Does that make sense? And the reason I would like to write down 5½ factor over here, just to remind you that we have that 5½ R as the C sub P. Okay, let me write it down here for you guys. So here. So remind you that C sub P is 5½ R. So at least you get the memory recalls a little bit that we did this back in the day of the constant pressure process. We have that extra 5½ R defined as the molar specific heat. Does that help? Okay. All right. That's just the way that I arranged, or not me, actually, the textbook, just the way that the textbook arranged the form of the heat during the constant pressure process. All right. But I'm showing you here is, what I'm showing you here is just like, if you don't worry about memorizing that formula, the 5½ thing, you can just go on calculating the change of the U, the work done, and then just add them together. You will get the heat during that process anyway. Okay, just want to emphasize that if you start from the, from the top, everything will look exactly the same. Okay, it's kind of nice. All right. Okay. Okay, so far so good. All right. Conclusion over here, during the heat during 3 to 4 is now heat is negative. What does this mean? It means heat flow out. Q3, 4. Cool. All right. And now you start to see, Ajahn, okay, now you can complete the whole thing by going back to the original point number 1. And once again, you are hitting with a constant pressure process. So that means if you want to go through the first law of thermodynamics from the beginning, what you're doing over here is you have to calculate the delta U and the W, and the W is just going to be area under the curve down here. You guys with me? From 4 to 1. But because you can see that you're going backward in volume, so it means the volume is decreasing. So whatever the area that you get down here, you're going to get the negative work done down here. Let me, instead of put the negative W, let me put it negative A 3 4. Does that make sense? 4 1, sorry. 4 1. The area under 4 1 line will give you the area, and then the work done from this process or this segment is going to be the negative of that value because it's the compression. The volume decreases. You get a negative work done. But all in all, when you have the delta U from 4 to 1 and the work done from 4 to 1, you add them together, you will get the heat flow from 4 to 1. And it's going to be just like we just discussed, 5/2 NR delta T for sure. You guys with me?
Okay.
Yeah, makes sense. Yes. All right. So that means now we sort of understand that the 5/2 NR delta T just come from delta U, 3/2 NR delta T, and the W, which is P delta V that we turn into NR delta T. Add together 5/2 NR delta T. So it's going to be 5/2 NR T final, which is 1, minus T initial, which is 4. And when we do the same trick, nRT is just P times V. So it's going to be 5/2 P at 1, V at 1 here, and here is P naught, V naught. Subtract out the P at 4, V at 4, it's P naught 2 V naught. So let me take that out. 2 P naught V naught. Yes, very cool. Alrighty. So what you can see over here is this subtraction will give you the negative P naught V naught. And just to, have enough space, having problem, but I think I did okay, squeezing everything down in one page here. So these two subtracted and then ends up with just a single term, negative P naught V naught. Here we go, guys. So at the end is a negative 5/2 P naught V naught. All right, it's hard to see, but that's at the bottom right corner over there. You can see now it's once again the heat is negative. So that means heat flow out. Let me put arrow right there. And that is the Q41. Complete everything. Okay, you guys with me so far? Okay. All right. So I hope this showcased everything that we have learned based on this diagram that we have. Right now, we know how to calculate the delta U, the work, the heat, and then combine them using the first law of thermodynamics. So now using this pretty much procedure, no matter what shape of the process you're looking at on the PV diagram, it's going to be just like this. There are only 3 things that you need to care about: delta U, Q, W. That's it. Okay. Now let's turn our attention back to this diagram a bit. Now here we go. What about the heat engine, guys? Okay. From the look of this one, so everyone seems to be okay, Dan. That's not bad. You're going from 1 to 2. You jump up in isotherm. Okay, let me do the highlighting. You jump up the isotherm. Then you expand it a little bit further. You still keep going up in isotherm. So it means temperature is rising, whatever. And then you jump down, release some heat, and then you contract the gas back to the original position, complete the cycle. Okay? And that's one cycle. And then the cycle repeats itself again and again. This gives you a heat engine. Okay? So let me redraw this diagram one more time. erase all those messy stuff here because I hope everyone understand what is going on now. So I don't think we need all this anymore. I mean, we still need it, but let me do it one more time. So what you get over here is heat flowing out. Let me call this Q41. Now you see what I'm seeing over here. Here. So this is exactly what we studied last time. Look at the main diagram that we have. Remember, we have the Q hot. You have to take in the heat. Oh, I mean, the graphic is lagging again. I think I know what's going on with the new laptop. I think the Wi-Fi card is bad. I think I have problem with the Wi-Fi connection with this new laptop. I think because the graphic shouldn't be a problem. I mean, it should have enough processing power for the graphic. But I think the way that it communicates up, send out the information into the internet and then post it on the Zoom and everything and broadcast to you guys just slow. It's just my complaining. Sorry, my bad. This is like this is the new one. I mean, it's just replace the old one with the one that's getting actually worse in performance. Dang. Okay. All right. Come back here. So now the main diagram that we have the hot reservoir, and you extract something from the hot temperature. It doesn't have to be a single source anymore now, but let's say that's hot. That's hot part. And then you dump things out in the cold reservoir. That's cold, right? Remember, this is our main diagram here. And what you really care about is just you want to redirect part of the energy to generate something useful. That is your work done by the engine. Do you see the similarity between these two here? Let me zoom in. See that? All right, so the main diagram, you can see that now there are two segments that the heat flow into the engine. There are two segments that the heat flowing out. So it turns out the flow in portion over here is going to be combined from these two parts. You guys with me now? All right, so this is the part that people sort of make mistakes from time to time because the diagram is so simple. We just say that, hey, there's a Q hot flowing into the engine. But in reality, the flow in of the heat might not come from a single source or a single process or a single part in your whatever cycle. It could be whatever, as long as the heat is flowing in. With me? Okay.
Okay.
So that means in this particular problems here, the Q hot is going to be the combination of the Q12 and Q23. Cool? Okay.
Okay.
Same idea. So that means now you understand what's supposed to be the heat that's flowing out. So now it's going to have Q34 and Q41. This is going to be your Q cold right there, the one that's flowing out. Okay. And once again, if you remember since the beginning that we calculated the work done, if you really want to find the work done from this cyclic process, at the end, your work done is going to be the area that is enclosed by this diagram. You guys remember sort of vaguely we did like maybe two of the problems that look like this. And that's because you have the work done from 2 to 3. That's the whole area underneath. But then once you go back from 4 to 1, you wipe out the bottom half of bottom part of this area. So you end up with the W that is just the enclosed inside this cyclic process. Yes. And because now you can see that the process going in clockwise direction. So going from 2 to 3, the work done over there is positive. Going back from 4 to 1, the work done there is negative. That's why you have a net positive work done at the end. And that's correspond to the cycle of a process that run clockwise. Yes, yes. So at the end, you guys know, wow, this whole thing is going to be positive, no doubt. And that is exactly what you expect right there. That is the work done there you want coming out of this. Okay, guys. So that concludes the whole relationship between the actual process that's showing up in the PV diagram and just the simple diagram that we use to explain any heat engine. Okay, so we have sort of like, the reality is more complex. All right, the main diagram is just simple, like, okay, you have a Q hot, you have a Q cold, and then the less it's just gonna be the work done. But the reality, you have to do a detailed calculation right here. But anyway, we have done all the work and everything is already just in front of you to answer. So can you guys now answer what is the efficiency of this engine? Well done, that's no problem. The efficiency is what you get or what you have to provide. Okay, so now you can pretty much take any description of the efficiency that you want and you can just go ahead, do calculation there. Okay. All right. Oh, that's a quick question comes in and it's a very good question. So there's a question asking Ajan, what if this cycle go counterclockwise? So the W will be negative, correct? The answer is yes. Very good. Okay. And that is actually what we studied in the process of refrigerator and air conditioner. So if you run this process counterclockwise, everything will go backward. The heat that's supposed to flow in is going to go in the opposite direction. The work done that's supposed to be positive will turn negative. And that is the heat pump. Very good, guys. Okay, guys, with me? So if you try to run everything backward, that is exactly what we studied before, which is like, okay, you have to supply the work done, extract some energy from the cold part, and then dump out at the hot. Very good. Cool. All right. So efficiency. All right. I ran out of space, but let me, all right, add a page right here. I should have done this long time ago. Why I try to squeeze things in here. I just add another page and be done with. All right. Anyway, so what we have over here is, oh, why don't we do this? Let me copy this part. I like this. Oh, will it? Oh, the figure might not come along. Ah, too bad. All right. But anyway, so I can just rearrange this myself. Whoa, what is going on now? Yeah, one more time. I think it's a bug in this software right here. When I sort of, yeah, there you go. That's my bad now. Okay. Give me a minute, guys. I don't know what's going on. Yeah. Some of you just say, why don't you use iPad or something? Okay, I have to write something down first. There you go. I don't know why. Okay, so what we have over here is now is good. So we have this main diagram over here. Okay, and just to mimic what we have over there, there's a Q come in from 1, 2. Okay, and from 2 to 3. And the heat flow out 3, 4, and another out at 4, 1, right? This is the main diagram that we have at this point. So the efficiency is just now depends on whatever definition, what expression you want to use. It could be W over the heat that you provide, and we only care about the magnitude of that. Or you can take saying that, hey, the work done must be the difference between the heat flow in, the heat flow out. Okay. And you can rearrange this one, make it look like this. Isn't that nice? All right. So up to you. Just pick one. Anything you like. Information, everything is already right in your hands, and you can do anything with it. All right. Even though we didn't do the work done directly, but it must be just the difference between the heat flow in and heat flow out. So just to be sort of make things a little bit easier, I'm going to pick this final expression over here in our calculation. So it's going to be equal to 1 minus Q cold. Q cold is the heat that's flowing out. So it's going to be Q34 with me plus Q41. See that? I'm just taking the magnitude now because all I care about is just how much. I don't care about the direction anymore because I already said, I know this is the Q that is leaking or get discarded out in the cold reservoir part. And then you divide it by heat that you have to supply to this engine is going to be Q12 plus Q23. Very good. All right. And now I just plug in the value that you already calculated. 3, 4, and the 4, 1 is going to be 3 P naught V naught. Okay, let me put it on the big bracket here. Plus, I just take the magnitude, right? 5 half P naught V naught. Cool? Yeah, that is going to be just the Q core part. Okay, the slide is lacking to you as well, I think. Is that right? Or is it just me? Yeah, I don't know. All right, divided by the Q flow in. Okay, Q12, just flash back a bit here. Q12 is 3 half P naught V naught. And for the 2, 3 is 5 half 2 P naught V naught, which actually can be rearranged here if you want. It's just 5. Okay, so just add those two together there. So it's going to be 3 half P naught V naught plus 5 P naught V naught. There you go. All right. Very nice. Very good.
Okay.
So far, so good. All right. So you just check. I just check my number here. Okay. I hope it's right. There you go. All right. One thing that you have to notice, never ever that you calculating the efficiency and then you end up with something that's not just a pure number. You guys with me?
Okay.
Efficiency must have your no units. So you're supposed to get just a pure number. What else? Right over here, it's going to be 1 minus. Okay, so let me work out the number a bit. It's a 3 plus 5 half. So it's going to be 11 over 2 on top. P naught, V naught. Just check my algebra as well, guys. Maybe I could do something wrong here. That's going to be 13 over 2, P naught, V naught. Yeah. Right. And as you can see, I have to make sure that these parameters or whatever is supposed to be disappeared from this expression because efficiency is supposed to be just a pure number. Okay. And that's it, guys. I'm done. 1 minus 11 over 13, and that is just 2 over 13. That is the efficiency of this engine. You can multiply 100, get a percentage of the efficiency. That is fine. Okay, up to you. Okay, so I hope you see pretty much everything that you want. And I can just emphasize one more time that the W, the area that enclosed by this cycle over here, definitely is going to be the Q12 plus Q23. And then you subtract out. Okay, let me put the bracket here just to classify them into heat flow in and heat flow out. Q34 plus Q41 for sure. There you go. All the time. It has to be. Everything must work under first law of thermodynamics that we have already seen is nothing more than just conservation of energy. All right. So you can calculate the W by looking at the area enclosed, or you can go through everything that we have just done. Just, do the heat flow in every segment, and eventually you can just loop back to the W calculation by taking the difference between heat flowing in and the heat flowing out. Everything must work out exactly just as expected. And that is done.
Okay.
Is it long? It takes like half the lecture just to, all right. But I mean, in reality, you don't need to spend this much time doing this because can you see how, the reason I'm doing this just to remind you what we have been doing in the past 2.5 weeks, right? However, if you really want to attack this problem yourself, you don't need to come this far. Whoa.
Okay.
Seriously, can you see how? So what I'm doing over here, it seems like I'm overworked. It's just a bit too much. The reason is because actually what I can do, okay, you guys follow my idea here. I'm going to write this diagram one more time, the process one more time, right? Okay. So the way, if I'm going to finish this problem, because this problem just asking you to figure out the efficiency, right? Well, even though in the exam, probably I'm going to ask you everything anyway, but okay, just in case, just so you know how to actually really apply this whole thing. So if you really want to just, go directly into the efficiency calculation, what you can do is just like, Ajahn, okay, you do Q12. That's doable. That's just the rate portion of this calculation right there. That's the first segment. You are good to go. Now you move on to the second segment. You say, okay, John, I'm going to get Q23, right? And actually, I can stop right here. The reason I want to stop here because I kind of know in my head, like, okay, I can double my work by going through the 3, 4, and 4, 1 segments, right? But the reason I say I can stop here because it's probably better for me just calculating the area inside because it's just simply just a rectangular area. And once I calculate that area, which, I mean, from the diagram, I know right away the area in here is going to be the width times the height. Okay. And everyone can see right away is, oh, Ajahn, the width times the height is just P naught V naught. It's so simple to calculate the W from this process. So what I can conclude right away is just like, okay, W is just P naught V naught. All right, you can add positive sign into it just to emphasize. And you already done. Why? Efficiency is just W over Q hot, which is Q12 plus Q23. And you are done.
Okay.
Can you see my point over here? Because we work everything under first law of thermodynamics, which is just the conservation of energy. So that means, all right, why we have to go through the trouble? Because I already knew sort of that Q12 is heat flow in, Q23 is heat flowing in. If I'm going to do the other two segments, it's going to be the reverse in directions because it's sort of like you're going backward, right? So you know that the rest of the segments will give you the heat flowing out. So, okay, I don't need to calculate those. I just calculate the work done, which is just simply just a rectangular area. And I just take the area of the rectangle, W, which is the work done, divided by the heat flow that you already calculated from the first two segments, and you are done.
Okay.
Okay, cool. But depends on the problems, of course. If the problem's asking you to calculate everything like, hey, what is the internal change from 1 to 2? What is the heat flow from there to, I mean, you have to calculate everything anyway. Okay. However, just showcase that everything has to work perfectly under the conservation of energy, which is the heart of the first law of thermodynamics. And that is
okay.
the conclusion of it. Cool. All right, guys. So I hope by showing you that, I would say this is the biggest scale of the question that you're going to get. All right. The rest of the question will be sort of, tiny, teeny stuff like, hey, okay, if I want to replace this with the Carnot engine, what kind of Carnot engine efficiency will be on and on. So that you can practice in the exercise. All right. But now we understand that the best engine in the universe give you a very simple conclusion that if you turn things into Carnot, the best engine in the universe, the only relationship that you want is just this. The ratio between the heat flow is exactly the ratio of the temperature among those two heat reservoir. And you are done.
Okay.
Cool. All right. So let's draw the line right here. I think that concluded the first law of thermodynamics. And we're going to take a break right here. After the break, I will take you to the second law of thermodynamics. And just to make your work a little less complicated, I'm just going to show you the basic idea of the second law of thermodynamics, doing some simple calculations, just like a sample, sort of like a maybe just like some simple system, and then how to calculate the parameters involved in the second law of thermodynamics, and just be done with. Right? Don't go too complicated in the second law. But I hope that I will get complex enough for you to see the essence of the second law of thermodynamics. All right, and that's after the break. Okay, I'll see you in 10. Sounds good? Okay, so welcome back. And what we are about to discuss next, and this is going to be the last portion of the material in the thermodynamics that we are looking at, and it's about the entropy. I think you have sort of like maybe have heard of this one from
Okay.
time to time. All right, especially last year, or is that 2 years ago already? The Tenet. I don't know. Have you guys seen this or not? All right, it's still a movie that I don't get it up to this point. It's still, all right. Christopher Nolan's movies always sort of like, give some complicated things for you to think after the movie. All right. And I think the number one movies of mine is still Inception. I think that's the number one. It used to be Matrix 20 something years ago. And it just like the fourth one just came out. I didn't have a chance to see it, but yeah, Matrix used to be my number one. Or even go even back further, it was like the Independence Day.
Okay.
I don't know, you guys maybe not yet born. Okay, all right, back out to our business here. Entropy is the quantity that pretty much, I would say, many of students and physicists ourselves seems like it's the concept that is so hard to explain in layman term. So it's mean for everyone that don't want to dive too deep into physics, when we talk about entropy, you will hear this word, the disorderedness. I don't know, have you sort of heard of this one before? All right, but anyway, just hear me out today. So the last portion of today's lecture will be sort of like, mostly relaxing. Just listen to me talking. And let's see, does that make sense to you? Okay, because I think maybe the main goal of today's lecture is just to give you an impression of what entropy is first, and then we're just going to do a simple calculation. When I say simple means we're just going to look at an example that allow you to calculate the entropy change. But to be able to do that, at least you have to accept what the entropy is first and what kind of property that entropy has before we start doing that particular calculation. Sounds like a plan? Okay. So think about this one first. And it's so weird. I don't know if this is a good approach or not. Let's think about this. If you have an isothermal process, because this is going to be the process that's easy to deal with because the temperature does not change. Yeah. So this is good. So delta T is 0, and that will render delta U to be 0 from the first law of thermodynamics as well. We are fine. So from the first law of thermodynamics, that will lead to delta U equal to 0, and that is Q minus W, so Q equal to W. We have done this. And if you flash back to the previous slide, we have already done the integration of the area under the curve, and you end up with nRT log V final over V initial. You guys remember this? Okay.
Okay.
That's not too bad. Everything came from isothermal process. So far, so good. So now we are going to dive a little bit deeper there. So let's say you are within this isothermal process and you look at just a fine, like infinitesimally small change. just, all right. So that means the amount of work done will be super, super duper small. We're going to call them dW, a tiny change of the work done. All right. So it's just like, you think of it like you expand the gas just a little bit. And we're going to do the same notation over here, even though it might not make sense to some of you, but why not? Just say a tiny amount of heat will exchange during this process, this infinitesimally small change over here. Let me name this dq. So from the result that we got from the isothermal process, nRT log V final over V initial. So what I can say right away, the dq that we're talking about must be the same as the dw that we defined over here from the first law of thermodynamics over here, right? Everything is good. Oops, sorry. Just right there. Yeah. All right. So far so good. And because work done is just the P delta V or PdV, and we already got from the result nRT log, that's sort of like V final over V initial, that was after the integral. But before the integral, you have dV over V. You guys with me so far?
Okay.
Yeah, this is the process at the beginning of the calculation that will lead you to your final result of nRT log V final over V initial. But now I don't want to do any integration. I'm just going to look at the change. All right. Don't have to add anything up just yet. Just take the look at the change. Now, when you look into this, there is something very interesting here. It turns out if you are focusing on this term right here, the volume change because you're doing some work with respect to the original volume. So it's a fractional change, or you can think like a percentage change or the ratio that's changed or whatever, but that is a relative change of the volume with respect to the original value. So if I'm focusing on just this ratio alone, that means all I need to do is I'm just going to turn the rest of this into the left-hand side of the equation. So your left-hand side will be left just dq, and then you bring the nRT to be on the same side. So far, so good. Haven't done anything. I'm just manipulation of, just a little bit of this and that, move things around. Here comes the interpretation of what is dV over V. And it turns out in the text, this implies disorderness.
Okay.
You guys confused? What does it mean, Ajahn, disorderness? When you have dV over V, what do you mean by disorder? Okay, so what I think under the context of disorderness or disorder is this. Think of like you have a playground and you have kids running around crazy and you are parents, for example. Okay. And then you say, oh, okay, you guys, all right, run around crazy, I'm just having a headache or whatever. But then suddenly the playground just getting extended. There are more rooms for these kids to run around, and kids just gonna go wild. It's just like, okay, we have more space. We have, I don't know, whatever. They just run even further away from you. And then you just like, okay, this is like chaos or whatever. I don't know. Does that make sense? So that means in terms of the gas, you have a gas running around in the volume V, but then suddenly, it doesn't have to be suddenly, but it means once the volume increases, there is some changes going on. Okay, there is some change in the volume. That change in the volume imply that the gas molecules has more volume to run around. So that means there are more ways for you to be headache about because now you have more volume to consider. Okay, so this is the reason why imply disorder. Okay, and then when you look at the right-hand side, so actually you can take into account this disorder by just looking at what is going on with the heat, temperature, and whatever the constant of that gas, that's fine. Okay, so when physicists look at this one, the only terms that seem to comes into the necessity or whatever seems to be a crucial portion that indicate this ratio is just this dude right here. The heat per temperature. What's so weird, right? But that's what it is. So it turns out the heat flow, all right, during this isothermal process. So you take the heat flow during the temperature at that particular point will define the entropy change. Believe it or not, guys. This is so weird. All right. But think of it. Okay. If we really take the concepts of disorder to be the meaning of the S, that's not a very bad idea because think about it. When you are fixed in temperature, we already knew if you add in the heat, you raising, eventually you're about to raise the temperature. If not, because you say you are fixed in temperature, that heat that flow in supposed to do something with the expansion of the system, right? Because that's what we only have. This is only two things. Temperature is already forced to be constant. So heat flow into the system will lead you to the increase in the volume. Increase in the volume, assume that you have more ways for these molecules in your system to run around. So this concept of disorder is not too bad. Okay, so we take this, the heat flow per, when you say per temperature, it's kind of weird, right? But anyway, so you can think of it as a ratio between the heat flow at particular temperature will signify the change in the entropy. Okay, but what's so good about this? The reason that this one is so good is because, all right, remember the reversibility and irreversibility? The heat is the problem. We already discussed a couple of times that heat is path dependent. It depends on path. You cannot just, talk about any heat. So when you want to go from point A to point B, you have to tell exactly how much heat you added or you extracted out from the system. It depends on path. So Ajahn, if that is the case, what is going to be heat that you're going to put into this equation here? Because there are like infinitely many variety of heat that you can throw in. It turns out it has to be the heat that calculated from a reversible process. Whoa, isn't that weird? The reason that is going to be just particular this reversible, because we already said every time you are dealing with irreversible process, the heat that involved with that one seems to be the heat that you lost forever. When I say lost forever, it means it's just going to be the heat that changes something already that you cannot take things back. Okay, so that means we don't want that thing because that thing is pretty much like sort of out of your hand. You cannot take that heat and do some manipulation, anything further anymore. So for this specific entropy, the term that we define, to have something useful later, and later means you want to keep carry on calculating this entropy on and on in some process that is reversible, that heat supposed to be a reversible heat as well. Then you come to here, it's just like Ajahn, and when are we going to know that what kind of heat that is reversible? Don't worry. We learned PV diagram. Whatever the curve that going crazy in the PV diagram from point 1 to point 2, as far as you can write that curve like that. Oh, it's supposed to be a single curve there. And that means you can calculate heat from here. And the heat that you calculated from this, which is the heat that we have been doing so far, right? All the heat and everything. So once you calculate the heat from the PV diagram, that is definitely going to be the reversible heat. Why? Because you can always change the arrow. You can go from A to B, or you can come back from B to A. Doesn't matter. Okay. Everything that we have done so far are quasi-static processes. So that means you do everything slowly, you can measure all the parameters nicely, and you can go forward and you can go backward as long as you specify the path, everything is good. All right, sort of go along with me up to this point. All right, so that is a real definition of the entropy change. You take into account the heat that calculated from any reversible process divided by the temperature during that change, you get the change in the entropy. Cool. All right, very nice. So if you want to take your system from initial point to final point, now all you need to do is just sum those change all together. Try to drag your energy from initial point to a final point. You eventually arrive at the total entropy change. So that's it, guys. This, you can think of this one as the way that you can calculate the entropy change in any system. That's it. Okay. That's the introduction, which you probably think gets anything. Like what? It's just like definition, right? And yeah, of course, if I just throw you guys with this equation, you're not gonna, okay, wait, it's another memorization. No, I don't want that. The key is this. It sounds like vague that I just like, hey, Dan, why physicists just introduce these terms? And then even though you try to lower our ends and lower, pretty much like try to tell the story about the volume change with respect to the original volume implied disorder. And then you look at the right side of this equation and they define this term as entropy. But the thing is this, it turns out it has some meaning that is so good. First of all, I don't know by accident or not, the ratio between the heat that is coming from the reversible process divided by temperature, it's a path independent. Whoa.
Okay.
All right. So this is the nice thing about it. So what you have over here is, it turns out S is path independent. Whoa. That is so cool. All right. So the good thing about this one is, all right, you can look sort of briefly about this, because when you look on the left-hand side, you already squeeze in the temperature along with the heat, and then you sum this whole thing into a single term of ds. So when you look at the ds, it seems like it only depends on this, which seems to be all right. The volume seems to be, I can't account for the volume. Okay, I can, measure the volume, fine. So that means you don't need to tell me how to measure the volume or how the gas get to this volume. So that means that's why the S is very useful, just like the energy. The energy, internal energy to be particular, is also path independent, right? Remember that, we like that, right? Because any energy, remember the mouse, you move it up, you come down, fine, no energy change. I throw this mouse to you, you throw it back to me, I put it at the original position, no energy change. Okay, so the cool thing about the energy, the concepts of energy, is it's path independent and make your life a lot easier to do everything. Same thing with the S. The entropy, it's also path independent. And that leads you to the idea of, okay, come back to the original position, nothing is changed. So if you have a reversible cyclic process, so it's cycle, right? Everything come back to the original position, you are guaranteed that, here, I put a circle here just to confirm that everything come back in full circle. You're going to get zero out of it. The change in the entropy of any complete cycle process will get you back to the original entropy and no entropy change. So delta S, or change in entropy, is zero.
Okay.
Okay, so conclusion about this one is, okay, S is path independent. So you can utilize S just like you utilize energy. And I don't know, it's like, this is the fun fact over here. Actually, physicists that working on this term, actually, he was intended to call this, to make it rhyme with the energy. Seriously.
Okay.
So they try to, like, because they assume that the entropy is supposed to be as big as energy. So they just come up with the words that sort of like go well with the energy. So it's supposed to have like energy and entropy and stuff like that. All right. But even though energy seems to be things that easier to understand. Okay. So what else? What does it do, Ajahn? And then why do we have to define another parameters or another variables into our universe over here? The answer is this, guys. Remember this condition here? Okay, you have a gas in an insulated wall, in an insulated container. So you do not allow heat to exchange, that's for sure. No heat flow, no work done because these containers do not allow to expand or anything. So in this case, this is a constant temperature process. Delta U is not going to change either because the temperature won't change. Nothing is changing. And then remember that we have a membrane that breaks, sort of like divide this gas into the bottom half and upper half. And then suddenly this membrane breaks. So the gas fill up the whole space. Yeah? That was a scenario that we discussed before. So the volume expands to twice, to twice as big. And of course, the pressure will drop in half because it's still P1 V1 over T1 equal to P2 V2 over T2, whatever. So when the volume is twice as big, the pressure will drop down in half. But temperature does not change. So the first law of thermodynamics does not give you anything. It's like delta U equal to Q minus W, but it's 0 equal to 0 minus 0. Do you see what's the problem here? But this is the process that happens in real world. This is normal gas expansion, fill up the whole container. But the first law of thermodynamics cannot take care of this because the first law of thermodynamics only say, fine, up to you. You go ahead. I mean, you're not going against conservation of energy. So I have no problem with that. But we have problem with that because we know going backward is not possible, right? We already agree on that. But first law of thermodynamics does not tell you this. Oh, maybe the arrow is too long, but the arrow, but the going backwards, the not what I can say. So the restriction that this process cannot go backward is not contained in the first law of thermodynamics. Start to see where we're going here. We need something else to guarantee that the nature can go only one way. And this is the way that it's supposed to go. And if you want to try to go this way, that's not possible. So you see this? This is not in the first law of thermodynamics. First law of thermodynamics allow this backward direction because it's not against conservation of energy. These two scenarios stays at the same energy. So now I'm going to show you how to calculate the entropy change from left to right. Okay. All right, you guys with me so far? So these two checks, first law does not help. I'm going to calculate entropy change from first point to final point here. Come with me here. Give me the PV diagram of this process, guys. Give me the PV diagram of this expansion process. Anybody? We're supposed to share the whiteboard and stuff and then have you guys draw on the board. That would be fun, yeah?
Okay.
But maybe not. Maybe nobody wants to participate. All right, so it's gonna be me writing alone. All right, guys, give me the PV diagram of this expansion. Mojan, let's go for it. P, V, initial volume, let me call it, that's a V. Sorry, it's just the same number. That's all right. At the end is 2V. So now we know it's an expansion. So if you're starting from the initial point, let me call this point number I, that's your initial point. So let's say your initial temperature is just some P naught. And then because you expand to twice as big, so you have to reduce your pressure down in half. You guys with me? It has to be still PV equal to nRT. It still has to follow this equation of states. So no problem. So that's your final point. What kind of curve that is going to connect between the initial point and final point in the PV diagram, guys? What do you think? This is not good. Not good. What kind of line, what kind of curve that connecting the initial condition of the gas and the final condition of the gas in the PV diagram? What do you think? You probably say, Ajahn, it's constant temperature process. And I told you all the time that every time I have PV diagram, please put on that isothermal line. So I know that these 2 points must be on the same isotherm because they're sharing the same temperature, correct? Very good.
Okay.
That's a very good argument. Yeah, I'm just talking to myself at this point. So I'm just saying that, Ajahn, why don't you just draw this? There you go. That is your expansion. Do you agree? To me, no, I don't. The reason I don't agree because this expansion process is the case that show you exactly what happens with the thermodynamics. The restriction that you had before, when this membrane breaks, bam, gas start to outflow into the vacuum, right? During this process, it's not going to be a quasi-static process. If you're waiting right here, let's say I'm waiting over here at the upper left corner, I'm still in the vacuum. My pressure is still 0. And then if you guys are waiting right here next to that pore, my pressure is supposed to be maybe it's pretty high because there's some maybe this gas just sort of exploding in front of your face. So the pressure is supposed to be super high. So that means on the top portion of this container during that breaking of the membrane, there's no equilibrium point. The pressure is not at the particular point that is stable enough for you to make a measurement, right? So in conclusion, going from initial condition to the final condition, I cannot draw any line. No, this is not a quasi-static process, guys. I don't know. And maybe PV diagram won't help me either because nothing can be written on the PV diagram because I cannot measure anything. You guys with me? Got the idea here? So how can I calculate the entropy change then? Ajahn, how can I calculate the entropy change then? If you don't even know the shape of the curve on the PV diagram. And here comes the conclusion that I'm trying to get you to, guys.
Okay.
With me? With me? The entropy change is path independent. I don't care. I don't care. I just know initial point is I, final point is F. You, me, whoever in this world can connect between these two lines, whatever they like. They can go like this. You know, they can go as crazy as you want. You can do isothermal if you like. Doesn't matter. As long as you're connecting between these 2 points and calculate the delta S from I to F, you will all get the same entropy change value. Isn't that cool? Got it now? Okay, so that is the utilities of the entropy. First of all, it doesn't matter. Pick your curve and calculate the heat over the temperature. You will get to the entropy change no matter which shape of the curve you pick. So if that is the case, which curve you're going to pick? Of course, and if I have a choice, I'm going to pick isothermal curve because it's already on the isothermal line, right? These 2 points are on the same isotherm. So what kind of process I'm going to pick? I'm going to pick the isothermal process that connecting between I to F. So let's do that. Here we go, guys. So what I'm going to do is I am connecting between initial point and the final point using any curve that is make it easy to calculate. Okay, and this one we already picked to be just an isothermal process here. All right, let's do it, guys. You can do anything you like. All right, you're starting from dq if you want. It's just the work done, and it's just the nRT dv over v. Okay, let me write everything down one more time. It's a p dv and p equal to nRT over v dv, right? This is what we started out with. And now you can do whatever you like. And if I want to go, you know, just like what we just did earlier, I'm just going to say, hey, Dan, let me write it as the dq over t is going to be nr over v dv. Yes. Very good. And this is already your change in the entropy ds. And if you want a full change of this one, you just do the integral from A to B, initial point to final point. Cool. All right. So over here, you can do that easily. So think about it. This is exactly what we get over here. I can write dq over t. T cancel is nr over v dv. You do the integral. The integral will give you, once again, n is constant, r is constant, 1 over v. The integral is log v. So you take the v of a and v of b, and then to be your limits of integration. Woohoo!
Okay.
Okay, and that's it. Because we know the volume at the final point is twice as big the initial point. So at the end is n or log 2. And that is your entropy change. That you will get this number no matter which line you try to connect. You can go as crazy as you want. Okay, that might be bad, but yes, you still have exactly the same n or log 2 entropy change. All right, so that's your freedom. Okay, but then you pick, you know, smart curve, you know, the curve that is smart for you to, you know, make you compute a little less. But what does this mean, guys, at the end? So it means this process has a positive change in the entropy. Isn't that cool? What cool that? The coolness of this one is every time that you see a change in the entropy, And as long as this one is, and I'm calling this an isolated system. So that means there's nowhere else for this system to communicate with everything else in the universe. This is it. This is pretty much your own universe. The gas in this tank, this is it. There's nothing else involved. There's nobody will come in. Nobody compress this gas down. You don't have any exchange of heat allowed. No, this is it. This is your isolated system. And the change that's going on within this isolated system give you a positive entropy change. You are talking about the irreversible process. Isn't that cool?
Okay.
Wow. Right there, guys. So this is the indicator that this process going this direction right here, give you positive change, is the process that won't go backward because this change has a positive entropy change. So what I'm going to about to conclude right here is this. Every time that you're dealing with the change in the entropy, whenever you have a positive change, that indicates irreversible process.
Cool. Okay.
All right. So that means the best that you can do is entropy is either constant. So that's mean delta S is 0 or delta S supposed to be greater than 0. That's it. For an isolated system, no way, no way that you will be able to get a negative entropy change. This is like crazy stuff, guys. It's supposed to be blown away. Okay, because this second law of thermodynamics linked to this quantity right here, the entropy. And because the entropy links to the heat that is reversible, and we stuck with the reversibility. Okay, so that means the change in the entropy will give you the idea of the reversibility of a process. However, because we just say that the change in the entropy never go negative for any isolated system. So the second law of thermodynamics is saying like this: the change in entropy of your universe. When you say universe, doesn't have to be the actual universe. It could be, this could be my universe right here. The gas in the insulated container, this is my universe. So it's an isolated system, that's what I'm saying. Must be greater than 0, okay, for, here we go, irreversible process. But the best that it can do is equal to 0. Believe it or not, equal to 0 for a reversible process. But because in our life, you have only 2 choices. This process is reversible or not. You don't have any other choices anymore. It's either reversible or not reversible. But because you already agree that any reversible process, delta S is 0. And for any irreversible process, delta S has to be greater than 0. So you don't have any other choices already in your life. So I'm saying we are living in the universe. Now, this is the actual universe. We are living in the universe that entropy is increasing, guys.
Okay.
Isn't that crazy? And you probably maybe heard of this one from, scientific article or something. We are moving towards heat death of the universe. Universe is expanding. And by the time that universe get all of the expansion done, that's the end of time. Believe it or not. So we should have problem with the time, because every time that you talk about the direction, and you guys know, like Ajahn, it's going forward, not going backward. People think of time because it seems like time is something that going in one direction, never go backward. And seems like entropy has the same thing. Entropy never go negative. It's stay the same. That's the best it can do, or going increasing. So it seems like everything seems to go in particular direction only one direction. So it's still debating actually. The concept of time and the concept of entropy, are they exactly the same thing or they are not? Or it's just a perception of human that feel like, okay, we still have people that think that time is still not real. Yeah, it's just, when you think about it, we don't need time. We don't need time. We only need something that is changing. And we just take that state of that things that it's changing to keep track of time. You guys with me? So that's a concept of the people that saying that they might not need time. You just only need some specific system that changing, constantly changing. And then you just check the states of that system. And then you can say, okay, there are something that is going on without introducing the time. However, there's another school of people saying that, okay, no, time is already stuck with the universe. It's something that going backward in time, going forward in time, even though it can go slow, fast, depends on general relativity, on and on, but it's something that is the fabric of the universe. Who knows? All right, it's just theory. We still don't really know what is going on, but at least what we are heading to, guys, we are heading to the end of the universe where the entropy just keep increasing. But once it reached the end of the line, it's going to be nothing. And that's the end of time. Woo.
Okay.
Is that good? Let's include the second law of thermodynamics, guys. All right, but anyway, for us, if you don't want to go that far, this is it. So this is one example that showcases you how can you actually calculate the entropy change. Even though you don't need to know the PV diagram or PV curve that's representing the change in reality, all you need is just, you can come up with any connecting curve that connect the initial point and the final point, and it's easy enough for you to calculate the heat over temperature. Go for it. Once you calculate the entropy change, you're going to get that number no matter which curve you picked anyway. All right. And just a fun fact for you guys. Okay. For those that come from computer science or computer engineering people, it actually has a meaning. This number 2 right here. It turns out if you split this into, it's already split, right? So you can see that what you have over here is when the up top over here has no gas, the bottom has gas. And then when the up top also has gas, along with the bottom has gas. You can think of it this way, right? So this is sort of like an information storage. This is a 1-bit system, guys. Right? Yes or no, yes or no, yes or no. It's 0 and 1, 0 and 1. So actually number 2 right here, it turns out to be, is 2 to the 1. So in the future, when of course, because quantum technology, quantum computing is sort of coming to you guys, and it turns out these numbers right here actually tells you the configurations. When you say configuration, mean, okay, Dan, I can see there are only 2 configurations. Is there gas on top or not? See, these are the 2 configurations, right? Yes or no, yes or no. So that means this system can store the information in 2 ways. Yes or no. So once you squeeze it in here, it turns out eventually entropy will have the connection to the amount of information that you can store in a system. So that's why in the data science, they represent the information capacity using entropy. So that is, entropy has some extra meaning to it. And so when you think about that, it's like, okay, that makes sense, because when things go further in time, given that we still okay with just a regular concept of time. So when you wait long and long enough, data that's flowing in the universe is going to grow, is keep growing. Data never goes smaller. Things get more complex. You guys getting older, the cells that you have is going to get age. You cannot get any younger. Your table's getting more chaotic. Right? First day, your table, your whatever, your house, everything looks nice and clean. But once you live in there for a while, you use all the times that getting, crazy stuff there lying around. you need some energy to rearrange your workspace. You have to, clean up places, all this stuff. But overall, when you do the cleaning, you sweat, you use your own energy, you're getting older, you get tired. So when you look at the whole universe, something is actually getting crazier. Okay, you're getting older, eventually we all have to die, and then everything just go into fine particle in the universe, and that's it. Everyone eventually has to have nothing left, and that is the end of the universe. Okay, so that's why the entropy is a very fascinating concept. It tells you the directions of the process that's going on in this universe. Cool, isn't that amazing? All right.
Okay.
I think I have told you enough. I guess it's maybe already too much, but I think this is very, very cool concept. I don't even know it's a concept that it's not a concept that physicists invented, but this is the nature. This is how universe works, and at least physicists can capture the change in the universe within the concepts of the entropy change. Okay, and that's allow you to understand why things going in one direction with no reversibility, and everything has to follow the second law of thermodynamics right there. Okay, all right, guys. So just to make a quick note, all right, even though there is a line over here that I didn't comment, but I don't want to go too deep into it because it's the equivalent saying that there's no heat engine run with 100% efficiency. But to be able to get the connection between the heat engine efficiency and the second law of thermodynamics, I think it would take too much, involved things that we have to consider. We have to go back to the heat engine consideration one more time, and I think that's going to take, or maybe you get even more confused. But anyway, just so you know that another reason that we won't get 100% efficiency, not just by that saying that we cannot reach 0 degree Kelvin. It turns out the second law of thermodynamics also inhibits the 100% efficiency engine as well. Okay. All right, guys. And that's close down the thermodynamics math right here. Woo. All right. Any questions so far? I hope you learned something. Yes. All right. So because now the rest of this, we have to decide when would you like to have the first exam be done with the first module. It's kind of nice. Okay. So I hope this works for you, and don't need to rush. You can take your time. Seriously, you can pick any date you want to do the first exam. Okay. So I don't know, you want to do the vote right now at this point, or I mean, I think this is a good time. You can just turn on the mic if you want, but you can, do it like 2 weeks from now. That is fine, or even 3 weeks from now, anytime you like. All right, just pick a date. All right, and any suggestion at all? You want to do it like during the weekend? Okay, the form of the exam will be the take home anyway, so it's gonna be 12 hours take home exam. All right, and I'm going to rely on your honesty. You're not supposed to, do it in group or whatever. At least it's a solo work. All right, so just respect yourself, on and on. So just stick with whatever you understanding, and then just do the work, and then you have pure, calm and peaceful time, 12 hours for you to complete the whole exam. So take your time. It's open book, open web, open internet, open universe, or whatever. All right, do anything you want. All right, just submit your exam number 1. Next weekend sounds good. All right, so let me propose this. Would you like to do it like you want it on Sunday? If you want to, that's possible. Okay. It could be like I mean, weekend. It could be on the weekend. For example, I can do like on the 5th, for example. So it's gonna be next Sunday, not this coming Sunday, but it's gonna be the Sunday after. Right? Sounds like a good plan. So it's like the 5th of February. That could be the one. You like this choice? And I can release the exam paper at 8 a.m. and then you have until 8 p.m. to submit your work. Or you can do it on Sunday if you like. Okay, or 6, that's fine. Up to you. Any preference? Feedback? Okay, make a poll in Google Classroom so people vote. Okay, that's fine. I will do that. Okay, so why not? So I'll create a poll, and then for those of you that has any problems, just comment on that poll. Sounds like a plan. Okay, all right. I thought it was just like in case that you guys has any suggestion in class, we all together, so it's kind of easy. Sunday the 6th. Okay, that's good. All right, you guys can just give me suggestions, so I'll throw that suggestion into a poll, and then the rest of the class can vote, and I will stick with that. All right, I like Sunday too, actually. But I don't know. Not from 8. What about from 12 to midnight? Okay, that sounds good. Yeah, that's fine. I can release the exam from noon, and then you go all the way. Yeah, because yeah, I understand some of you might not be like a morning person. So so all right,
Okay.
stick with the I mean, you guys are young, so you work late. So I can release at noon and you have until midnight to submit. That sounds reasonable too. All right, maybe I'll put that in a poll too. But I'm definitely sure you guys like starting from noon better. I'm sure. All right, 12 hours is way too much already. You're supposed to get the exam done in like an hour or something, 2 hours at most, I guess. All right, don't worry. 12 hours will be plenty. All right. Noon is good. Have a class on Sunday. Oh, yeah, yeah. For example, that some of your friend has class on Sunday. Good. All right, so let's go for noon to midnight. And about time, I will create a poll, and then you just do the vote, and you guys can see the results, and then we can discuss further from there. All right, but at least it's gonna be, let's say, 2 weeks from now. Sounds like a plan? Yeah. So don't worry about this exam as of now. Next Sunday, we're just gonna keep going studying physics. All right, but then you can, prepare for the exam week later. Okay, guys. And that is it for today, and of course for thermodynamics part. And next time we're going to dive into something else. Go back to mechanics a little bit. Talk about wave. Okay, very good. All right, I got some comment. Very nice. Okay, seems like Sunday seems to be a choice. All right, guys, thank you so much.
Okay.
And I will see you guys on Monday, right? Next Monday. Thank you very much. Bye-bye.